Hello, in this video, we will look into real numbers. As introduced in the previous video, real numbers are defined by four main axioms. The first axiom is about addition. The second axiom is about multiplication. The third is about comparing the sizes of the real numbers. And the last is the axiom known as the completeness of real numbers. Our goal is to define the entity called a real number as an interface in the Go language, that is, as an abstract type. However, we are not trying to map each axiom one by one to methods in the interface. This is practically impossible. To implement these axioms as methods, we need to understand the functionality of the axiom. For example, the core functionality of the axiom on addition of real number is that addition can be performed between any two real numbers. Similarly, the axiom on multiplication of real numbers has the functionality that multiplication can be performed between any two real numbers. And the axioms on comparing the size of the real numbers has the functionality that the size between any two real numbers can be compared. Here, we will implement these as methods. Let's start by defining two interfaces called additive and multiplicative. The additive interface has three methods: add, add-inv, and zero. First, let's look at the add method. The add method is a method that returns the sum of two variables, the color of the method, and its input. On the other hand, it calculates the sum of two real numbers. Now, let's examine the format of the add method. The add method states that both the input and output type must be additive. This additive refers to the interface type that is currently being defined. At first glance, this might seem like a paradoxical definition, like circular logic, but it is not. The additive type acts as a wrapper around static type, like struct type. The add method checks whether the input is wrapped as an additive type. In other words, as long as input type implements the method required by additive type according to their names and formats, it's fine. Both the variable that calls the add method and the input variable are of the additive type, but their actual static type can be different. Now, the add-inv method is a function that returns the additive inverse, that is, the negative value of the variable that calls it. This does not require any input. Lastly, the zero method is defined for a slightly more practical purpose. Let me explain a bit more about what this means. As you will see in the code introduced later, this additive interface is like an empty shell. An empty shell cannot create another empty shell. However, sometimes you need to return data wrapped in the same empty shell with the specific contents. To generate the contents, you either need to examine the contents of the input or use the method that the shell possesses to create new content. The zero method wraps the real number containing the value 0 in an additive and returns it. Next, let's look at the multiplicative interface. It requires a method related to multiplication operation called mul, a method to create a multiplicative inverse called mulinv, and finally, a method to create a multiplicative identity called 1. Now, let's implement the real interface, which represent real numbers. This requires three interfaces: element, additive, and multiplicative, along with two additional methods. First, the real interface requires element interface introduced earlier. This means that it is comparable entity and it has equals method. The addition and multiplication of real numbers are implemented through additive and multiplicative interfaces, respectively. As we saw earlier, any two real numbers must be comparable in sizes, so the greater than method is required. This returns the result of comparing the sizes of the variable that calls it and the input variable. Lastly, the toFloat method is a practical method. No matter how abstract the type of real number is, since it is a real number, the user must be able to know its magnitude. The toFloat method returns this in form of floating point number. So, what can we do with this real interface? Obviously, integers are a special kind of real number, so the real number interface should be able to generate integers. So let's create a function that generates integers. Generally, integers such as 1, 2, 3 are the integers that we are familiar with. They are also the integer in the real number system that we are familiar with. And such real numbers are represented by decimal points or floating points. Here, we only have the interface of real number, and it is merely the empty shell. We do not know what data that the user implemented with this interface, and we do not know what's inside of it. Integers are numbers that can count like natural numbers. From this perspective, the integer function should be able to return nth integer in the same kind. In order to get such integer, we need to use the variable f, which is supposed to be implement the real interface. If n is 0, this naturally means that it is the additive identity that is 0, so it returns the result of 0 method as it is. If n is not 0, it first determines whether n is greater than 0 or not. If n is greater than 0, it adds the multiplicative identity 1 n times, and if it is less than 0, it adds minus 1 n times and returns the result. In addition, we can also define a function that returns a rational number. Rational is a function that returns a rational number like a over b from a given array of its input type. Since a over b is ultimately the product of a and the inverse of b, it can be implemented in this way. When writing or reading a function that has an interface type as the input, the important thing is not to try to figure out what the contents or value of the variable are, but to understand how its methods were used. Now, let's implement a function that calculates the square root of a given real number, which is a slightly different example. We name the function after its abbreviation sqrt. There are many ways to calculate square root of a real number, but here we will introduce as it is the limit of a sequence defined by following recurrence relation. We are trying to find the value where the square of the sequence term xn becomes indistinguishable from a. This is specified in the loop condition of the sqrt function. The recurrence relation requires a rational number 1 over 2, so we define it in half. The loop in the function is the process of continuously updating the value of the variable x, which was initially set to 1. Now, let's actually implement the real interface. Here, we will redefine a type called simple real as float64. First, simple real implements the element interface. It has the equals method. The equals method takes an input of type any and determines whether its value is the same as the simple real type f that calls it. At this point, it checks whether the difference between the two values exceeds a certain threshold. Here, the threshold is defined as epsilon, a global variable set to be 10 to the power of minus 6. If the difference between the two numbers exceeds this threshold, the two numbers are considered to be different. Next, the greater than method compares the result of converting the caller value and the input value to floating point number. ToFloat method returns itself by typecasting. This is possible because content of simple real is already of type float64. Next, the additive interface is implemented as follows. First, 0 wraps the value 0, which is of float64 type, with a simple real and returns it. Add converts the input to float64 type and returns the sum of the converted value wrapped as simple real. Note that simple real is assumed to be defined in a package different from the root package where the additive interface is defined. What is important here is that simple real must have methods with exactly the same format as those defined by the additive interface. In other words, the input and output type should refer to the additive type defined by the GoCloud package, which is the root package. So the prefix is added in this way. Replicative can also be implemented in a similar way. Let's pay attention to boolean here. If the value of color variable is 0, its inverse does not exist, so it returns nil to indicate absence. So far, we have observed how real interface is implemented. In the next video, we will look into the concept of vectors. Thank you.